question 60 in chapter 10 of our physics textbook. It talks about how a shooting star is basically a meteor that is being tracked as drag slows down the meteor, converting kinetic energy into thermal energy, which is like the glowing trail that we see behind the meteor. So it talks about how typically a meteor has small mass, but it makes up for it in speed. So the question it has is, assuming that the meteor is 1.5 grams and is moving at 50 kilometers per second, what is the power generated from the meteor if it slows down over 2.1 seconds? So to start this problem, what we have to do first is a couple conversions, because we have it in grams and kilometers when typically in physics we operate with kilograms and meters. So to get to both of those values that we need, we take our 1.5 grams and divide it by 1,000 grams to convert it to kilograms. So we get 0.0015 kilograms. And then for the meteor, for the speed of the meteor, we have to take our 50 kilometers and times it by 1,000 to get it into meters. So we get 50,000 meters, and then it was kilometers per second, so it's going to be meters per second. And so that gives us both our mass of the meteor in kilograms and our speed of the meteor in meters per second. So now that we have those units converted, what we can do is use this equation here, because it talks about how the kinetic energy is converted into thermal energy. So the formula for kinetic energy is K equals 1/2 the mass times the velocity squared. So once we input the values we have, we should get the 0.0015 kilograms, which is the mass, times by the velocity, which is 50,000 meters per second squared. So once we run this through our calculator, we should get joules. So we should get 1,875,000 joules, which is the kinetic energy from the meteor. So now what we need to do is, it says that it converts it to thermal energy, and it wants to know what power basically is generated from the meteor if it slows down over 2.1 seconds. So to get the power that is generated, we just need to use this formula, which is the power equals energy over time. And so we have our energy here in joules, and it gave us the time in the problem, saying it takes 2.1 seconds for it to slow down. So all we simply need to do to get the power is divide our energy, which was 1,875,000 joules, divided by 2.1 seconds, which will give us so our power will be 892,857.14 watts, which is the unit for power that we use. And so to answer the question, that's the amount of power that would be generated from the meteor if it slows down over 2.1 seconds. And then the second part of the question that I asked is, can you see why the tiny object can make a glowing trail that can be seen from hundreds of kilometers away? And the answer to that would be yes. And the reason why is, we think about it like a typical light bulb that doesn't have very many watts and can still light up a room pretty well. This amount of watts generated from the meteor would be well enough amount of light provided for us to be able to see it from thousands of kilometers away. So due to the fact that this is just such a large value, we can definitely see like how we get enough basically power generated that we can see it so far away. And so that's question 60 in chapter 10 of our physics textbook.